Well, here we are once again. It's the physics video lecture. Physics 107B video lecture 16. So I had some interest in the problem chapter 9, problem 40, the resonant cavity, completely blocked off resonant cavity. And as good a way as any to wrap up chapter 9 and move on into chapter 10. So let's go ahead and have a look at that. The resonant cavity and its frequencies. Okay, so let's get started here. So this is problem 940. And let's go ahead and orient like this. Here's our X, Y, and our Z axis. And the cavity now, X goes to A, Y goes to B, Z goes to D. And what's the perspective on this box here? Something like this. Point is that it's, perfect conductor, it's a box, A, B, D. So we have to solve Maxwell's equations for this. And what do we ask for? Okay, I'll go ahead and write that we have 0 less than or equal to A, no, X less than or equal to A, X, A, 0, Y, B, Z, D, and then the frequency, the resonant frequencies of the transverse electric and magnetic modes, omega sub L M N C times pi root, just write out the book, L over D squared plus M over A squared plus N over B squared. L, M, and N are just the integers. So what we're going to do is find the electric and magnetic fields sufficiently generally, E and B. And we have to find the fields, make sure they satisfy the boundary conditions, and then we can talk about what happens after that. That's pretty much what we have to do. So let's see. So we're looking for solutions. I can put this all on the first board. Solutions of the form. And this is what we've been working with. Except before we had it say an infinite channel. This time we have the thing boxed off. So E has to be E0 of X, Y, and Z. E to the minus I omega T. And the same thing for the magnetic field. Okay. E0, X, Y, Z, e to the minus I omega T. Good. Anything else there? Oh yeah, and the boundary conditions. At the boundaries, which are the walls of the box, parallel component of E vanishes, and the perpendicular component of B vanishes. So the first thing is what we're going to do is write down Maxwell's equations, and then we'll see that one of them tells us that as long as we find the electric field, then we'll get the magnetic field just by taking a derivative. So let's write down Maxwell's equations. And it's a vacuum with boundary conditions, so we just have the vacuum Maxwell's equations. So Maxwell, we have divergence E equals 0, divergence B equals 0, curl of E equal to minus dB dt, and the curl of B is equal to 1 over, I'm going to write mu naught epsilon over c squared. I'm writing c squared, fine. So good, we have equations 1, 2, 3, and 4. But we've been here before, so I can actually just point out, we know that we can plug these into each other and get the wave equations for E and for B. Now, with this trial solution, you can see that curl of E will be equal to, well, let's just see what we're going to have here. We're going to have curl of E0, which is just the spatial part. It's going to be equal to minus dB dt. So we'll have I over omega, I omega over C squared. Wait a minute. Back up. So we're going to have the curl of the E0, and the dB dt is just going to bring down I omega. Minus times minus plus I omega B0. There we go. Right. So there we go. We just have to take the derivatives of our E, and then we've got our B, right? Divided by I omega. So that's good. So yeah, I can note already it suffices to find E0, X, Y, and Z now because of that. And we've already seen a couple of times that we just have a wave equation for E and for B. So plugging these equations into each other, we get the wave equation. So next, let's just write down our wave equation. Equation for the vector E. So we have d squared E dt squared C squared del squared E. Okay. So that's 3 equations, Ex, Ey, and Ez, and we'll actually see that if we just write down the equation for Ex and solve it and ponder a few issues, it'll suffice to find E sub x to just write down the other ones. So we're going to do the same thing. D squared E sub x dt squared is equal to C squared del squared E sub x. So this is the one we actually have to solve. And then we'll try and make sure that everything else follows out of that. Okay, but yeah, this is still our trial solution. So we have the standard minus omega squared Ex or E0. Well, I'm just going to write Ex. Okay. It's understood now that the Ex is the E sub 0x. I'll save writing that thing there. So is equal to C squared, and then we've got the del squared E sub x. The E sub x is still a function of all 3 variables. So x squared E squared y squared E sub x E squared E z squared E sub x. So at this point we have to do some kind of a trial solution, and we're going to do separation of variables such that we have a function of x, a function of y, a function of z. So I think we did this, we've done this a couple times. just remember this stuff. So what we have here is minus omega squared over c squared, and then this xyz, capital X, Y, Z on the left side, and on the right side, we divide by c squared, we have x double prime y z plus x y double prime z plus x y z double prime. And we do the standard dividing everything by x, y, z. Those are the functions. And then we have, I'll just show it for x, we have x double prime over x. Same here, y double prime over y, z double prime over z. And this is going to be equal to, since the left side is clearly negative, then these will all be negative constants. And because they're, it's a standard argument, because they're independent, they have to be independent of each other, they each equal a constant. Okay, and it's negative, and you pull out the negative sign and declare that to be squared. Okay. So yeah, we have all right about. We have y double prime over y, okay, y squared, z double prime over z minus k, z squared. Well, these are just sines and cosines, right? X double prime minus kx squared x. We're just going to look at that. And just construct what we get. So now our function that we were looking for, I need some room to write this thing. Let's see what happens. So e sub x, x, y, z. We're going to have a sine kxx plus b cos kxx. And then we're going to multiply by c and b, so c sine ky times y plus b cos ky times y, and then kind of multiply and cde sine kz z plus f cos kz times z. Okay, so there we go. Got a lot of undetermined constants here. So what we can do next is consider the boundary conditions. Next. Boundary conditions. Here maybe we should draw our box again. Why not? So again, we've got the x, y, and z. And remember, we're looking at e sub x. So that's the field component in the x direction. So the parallel, right, e parallel equals 0. The parallel aspect, since we're pointing in x direction, oh, this is y, is say at the ends of the box, z equals 0 and z equals d. Okay, so at z equals 0, z equals d, and the same thing b equals 0, no, y equals 0, y equals b. Okay. So if we're out here, let's see if we can draw our box again. There's a box. So if we're out here, if we're here at z equals 0, that's that plate on the end of the box. You can see that the x component is a parallel component. And the same thing with the y component. The x component is parallel at y equals 0 and at y equals b. Because it's pointing this way. Because the x component, right, is pointing that way. So that's what we're going to use when we evaluate this expression right here. Okay. Erase this. I think I can draw that in red. My picture has any perspective to it, but here at the end, our E would be like that. That's parallel to the boundary. And here at y equals b, think of these as being on that face. Okay. So those are our boundary conditions. Now let's evaluate them. So we have these trigonometric functions here, and so when y equals 0, okay, that's trivially 0, but the d cos kyy is not trivially 0, so that's going to have to, the d is going to have to be equal to 0, and same with the f right here. On the other hand, for the x components, we can't say that. So this criterion with the boundary condition has gotten rid of the d and the f. So this means d equals 0, f equals 0, and we now have, for our ex, is going to equal a sine kxx plus b cos kxx, and c and e that remain, we can just let them be equal to 1 because we already have constants up here. So then we have just sine kyy sine kzz. And for these to satisfy the boundary conditions, at b, at b and at d, we have to have conditions placed on these as well. So we have ky times, the y is the b, times b is equal to, and now I forgot what constant I used, the b, or the index I used. The b's I used for the n's, okay, so kyb is equal to n times pi, and kzd, and for d I use, or for z I used l, okay, equals l times pi. N and l are integers. And obviously, we're going to do the same thing for ey and ez. They're going to start out with the same form. And for ey, we're going to retain this pair. And for ez, we're going to retain this pair with the ky and the kz's respectively, okay? So we don't actually have to write them down, we're doing fine here, but by that argument, we're also going to have kxa is equal to n times pi. Same as here, in order for these signs, in order for the functions to vanish at the boundaries, okay? So yeah, that's how we pick all of these up. Good. We're not done with this yet. So now we have the general form, and the same thing is it's going to be very similar for EY and EZ. Yeah, I'll just state it, okay? EY, EZ. But by the same arguments we made with those parallel components, for the EY we're just going to end up with the sine kxx, but then we're going to have this bracket here with kyy and cosine kyy, okay? And then kzz, and for the EZ we're going to have, in other words, just change the names. Just change the name to x, y, and z, and you get something analogous in each case. Okay, good. The next aspect that we have to deal with is divergence of E is equal to 0. And that's, of course, dEx dx, dEy dy plus dEz dz. So for that to equal 0, let's just look at this first one here. We're going to have this bracket here, a cos, okay, we're taking derivatives, so a times kx cos kxx minus a sine k, or a kx sine kxx, and then a bunch of other stuff. For this to vanish at the ends even, we have to get rid of A. We have to get rid of, well, this must have been B. This was B. Okay, but by taking the derivative, we have to get rid of the A here. This one's not going to vanish at the endpoints even. And so we get rid of A equals 0. This was times other stuff, so evaluate at, x equals 0, for instance. And these are, like I said, it's analogous to the ones I just wrote down. So what that does, though, it makes this constant A be equals 0. Now we can actually write down EX once and for all. And what did I do? I used the letter B. So we finally get, and this one we'll focus on a bit, D, we have, this is what was left, so cosine kxx, sine kyy, sine kzz. Okay, let's put a box around this thing. And what is it going to be for E sub y? Well, we'll have another letter, C. And then we'll have the sine, cosine for the y, sine for the z again. Okay, you can see the pattern here. Again, you can just do the other couple permutations because, just renaming these. So did I write all of those down? Actually, in my notes, I wrote them all down. So I'll do that for you here too. May as well. So yeah, then you can see we're going to have E sub y equals some constant sine kxx cos kyy sine kzz, and then for E sub z we'll have some constant d sine kxx kyy cos kzz. And there you have it. Those are our fields from which we should be able to assemble everything else that we need. Okay. Anything else to say about that? Yeah, okay, just a moment. So I'll go ahead and get rid of this. And I think everything will fit on this board that I want to say in addition to this. So those are our fields. Now let's remind ourselves, these are E sub 0 of x, y, and z. E of x, y, z, and t is of course this E sub 0 times the e to the minus I omega t. Okay, so then you have that field, and B, and we had B would have been, or B sub 0, since we just take it out of the curl, would be 1 over I omega curl of E sub 0. Right, and then B is B sub 0 e to the minus I omega t. So then you have those fields. If you want your transverse modes, then you kill the z component. Okay, so yeah, you can get everything you need off of this now. And finally, I have room right up here. Remember we had omega squared over c squared kx squared plus ky squared plus kz squared. So we have everything in place now. So that's where we have omega is equal to c, and we're going to have a square root, and the kx squared will be n squared pi squared over a squared. So pi will be common, we'll pull it out, and then we'll have our n over a squared, and then our b. One of these was supposed to be m, huh? Which one was m? M went with the a, so m over a squared plus n over b squared, n over b squared plus L over D squared. N, M, and L are just the integers. Okay. And everything else you can construct now that you have these expressions here. In fact, there would be a few more things to construct to get everything explicit, because these are the complex expressions, and if you want to take it all the way to the real part, you could do that too. But I think we'll leave it at that. That's an interesting problem. Good way to wrap up that chapter. In fact, this is a really standard expression later on when you just talk about the normal modes of the electromagnetic field. Say in some space with periodic boundary conditions, this will actually be the expression used from here you go on to sending your volumes out to infinity and so forth. So this is a good one to remember. Please remember that it exists. And we're ready to move on to the next chapter. Let's see what the clock says. Okay, excellent. So what we've learned is, and saw it for the last time here, Maxwell's equations have as their solutions electromagnetic waves. The next chapters are about generating electromagnetic waves out of accelerated charges. Right here we've just taken the waves in vacuum. We also took the waves in matter when we could turn the equations into equations similar to the waves in vacuum with different constants. But now we're going to go to where the sources exist. So we're going to write down Maxwell's equations with their sources again, the charge density and the current density, and then work on the formulation. Good. And what else should we say here? So this is the next chapter, potentials and fields. Okay. So we'll just start with what I had said here, Maxwell's equations have wave solutions. And we want to find the origin of these in the motion of charges. So how is radiation generated? How about that? How is electromagnetic radiation generated? Good, so let's write them down. First of all, divergence of E with the sources now, rho over epsilon naught, divergence of B vanishes, curl of E minus dB dt, and then Ampere Maxwell, curl of B, and U naught epsilon naught. Yeah, we're not writing the speed of light in here right now. So just mu naught J plus U naught epsilon naught d E dt. So yeah, this time we have the sources in place, rho and J, and what we're going to do is try to express everything in terms of the potentials. So express everything in terms of A such that curl of A is equal to B, and V such that gradient of V is equal to minus E, or minus gradient of V is equal to E. So our strategy is just to substitute these expressions into Maxwell's equations and see where it leads us. Okay. So we'll start with the third one here. 1, 2, 3, 4. We'll start with the third one. So we have curl of E minus d over dt, and now we have the curl of A. So what we can do is write curl of E plus dA dt is equal to 0. Put that grad in there right now. Yeah. And then, since the curl of the gradient is 0, we can specify E plus dA dt is equal to minus the gradient of V. And in fact, where's my first equation? Yeah. Well, I'm gonna have to rewrite these. But I already have a condition, so I do want to rewrite it this way. Here, let's got room on this board. So here I had my D field too. We're looking to express things in terms of the potentials, but of course we want to be able to get the fields from the potentials. So here I started with this definition, so that's actually good enough. Here we're just going to say what E is. So E is equal to minus gradient of V minus dA dt. Just so we have those relations. So if we found V and A, we have found E and B. Good. Am I numbering these? Maybe. 1, 2. So let's see, what's our next step? We use equation 1, the divergence of E. So now for the divergence of E, so next, use equation 1. Divergence of E is rho over epsilon naught, or minus div grad, so minus del squared V minus d dt of the divergence of A is equal to rho over epsilon naught. So this one I think stands on its own, right? Yeah. And, well, in the book they have the plus sign, so let's go ahead and do that. Get rid of the minus signs. Good, so this one actually stands on its own, or stands here as well. Again, you have V and A, and these are your actual sources here. So the last one we can plug in. So for the last equation, curl of A, so for 4, we use curl of A is equal to minus del squared A plus grad div A. Okay. We use that identity, so that B in terms of A, we're going to have a div A here, and then the mu naught epsilon naught d E dt. So we're taking the time derivative of this. dE dt, you're going to see we get a del squared A dt squared. I'm just going to write down the result and then point at it. Yeah, with the signs the way we want them. So we're going to have a del squared A minus mu naught epsilon naught d squared A dt squared vector minus the gradient of div A plus mu naught epsilon naught dv dt minus mu naught j. You can actually see where all those come from. So I'll put a box around here as well. These are our new Maxwell's equations. So yeah. Right, we gave everything a minus sign, the curl of B, curl of A, so there's your del squared. There's your minus grad div, okay, give it a minus sign. Grad dv dt grad div A is the dv dt. Oh yeah, the dE dt, there we go, dv dt, yeah, it's all there. Good. So I could keep numbering these. 3, 4. So these are the differential equations we have to solve in order to get A and V with sources. So these are the two equations with the sources, and these are the two equations that give us E and B if we have found A and V. So this is a vector equation, it's 3 equations. This is a scalar equation, it's 4th equation, and we have V and A are 4 quantities, okay? So there are differential equations to solve. Okay, let's consult the clock. Okay, perfect. So these are the equations that replace 1 through 4 up there. One, 4, Maxwell. And in particular, these equations 3 and 4, 3, 4 are 4 equations for A and V. Okay, what's next? We've got half a board here. So there's a really interesting thing that we have to explore now, and that is due to the fact that V and A all appear under derivatives. So they're not uniquely determined, at least up to a constant, right? But it turns out they're determined up to what's called a gauge transformation. But you see it trivially because they're all under derivatives. We actually have something like that in classical mechanics as well. So that's the next topic, is gauge transformations. Let's see where we are here. Yeah. Okay, yeah, here we go. Our new equations do not uniquely determine determine unique vector potential and scalar potential. And we're already accustomed to that with scalar potentials for sure. But what we can do is we can have a scalar potential A prime equals A plus the gradient of some function lambda, because curl of the gradient is identically equal to 0. So if we take the curl of A prime, we have the curl of A plus 0. So good, we can add an arbitrary gradient of some function to our vector potential. That'll then have consequences for the scalar potential. So I think the best way to do that, we can skip a bunch of steps. This is actually pretty direct. Yeah. So we look at E now. Since E and everything's up there equals minus gradient V minus dA dt, minus gradient of V minus, now we'll just plug in what this A is here. It's A prime minus d dt of A prime minus gradient lambda. Okay. We got room here? Okay, so equals minus gradient of V minus times minus is plus lambda. I'll make sure I got the signs right. No. So I've got a minus sign here, so I have to have V minus, yeah, d lambda dt. Okay, crucial step right here. No big deal though. Minus gradient. And then I have minus d a dt. So I'm going to get the same E field if I have, instead of my potential, I have potential minus d lambda dt, where this lambda is the same function right there. So that allows us to set up our gauge transformation. Put that right under here. Actually, it's up there, but we'll just showcase it. So what we are looking at is gauge transformation, and A prime is equal to A plus the gradient of a lambda, B prime is equal to B minus that d lambda dt. So what we're looking at is lambda of x, y, z, and t, and apparently it's quite arbitrary because of these identities here. Curl of grad is equal to 0. So arbitrary function. See how we're doing time-wise. Yeah. And what we'll see is we can make use of these conditions to simplify these equations. After all, they look pretty complicated, these two. But Yeah, actually what I want to end up with is a discussion of the gauge transformation in classical mechanics. We can tie something together really nicely here. Yeah, and that'll tie in exactly to what we have here. So let me go ahead and do another board or so. The gauge transformation in classical mechanics, specifically in Lagrangian mechanics. So let's say recall the gauge transformation in Lagrangian mechanics. That was the following. What we had was L Lagrangian as a function of the coordinates, the generalized coordinates, generalized velocities, and time. And then what we find is if we have L prime, just like what we're doing here, equals L plus the complete time derivative, the complete time derivative of an arbitrary function of the coordinates and the time. What we find is this L prime here will still give you the same equations of motion. So yeah, if L and L prime simply differ by a complete time derivative of the coordinates and time, then we have the same equations of motion. And it's actually worth writing those down. Yeah, let's keep those up there. Worth writing, in fact, we'll keep these up here as well. Worth writing the Euler-Lagrange equations down because it comes from a similar situation here, of course. So the equations of motion, namely time derivative dl dqi dot dl dqi equals 0. Right, these are the equations of motion I equals 1 to n. And it had to be the case, at least to some degree, because again, L, everything that appears under a derivative. So at the very least, you had to be able to add a constant here, okay? And a complete time derivative of the constant would be c times t. So we would, the trivial case we would already see just like we had here. Now, the Lagrangian for a charged particle and non-relativistic charged particle, I guess we have to say that, relativistically or non-relativistic charged particle. Okay. Charged particle. This is one we work with in mechanics, and it's very interesting. We have L, we just have the kinetic energy minus QV plus, we can do it just with Q A dot V, where E equals minus gradient V, and not to, don't mistake the V for the velocity there, it's a velocity, and V equals curl of A, and T here is just the regular kinetic energy, half mv squared. So what we do is we take this Lagrangian and the Euler-Lagrange equations and we get it delivers mr second derivative equals q e plus qv cross v. Okay. So that's what you get in mechanics. But the gauge transformation also works right here. So let's do that. I guess I'll erase these now. We'll end with that. We'll have the gauge transformation up there. So yeah, this is a fun problem. Euler Lagrange equations. It's clear enough. QE, QB cross B. So yeah, the final thing we want to do now is to ask, what about that gauge transformation? And yep, everything that we need is on the board. So now check the situation with A prime and V prime. So what we'll do is we'll make that substitution. We'll have this L prime, kinetic energy minus Q, and the V prime is going to be V minus d lambda dt, and then Q, the A prime is going to be A plus gradient lambda, and we're going to dot that in the velocity V. So what do we get? We get L prime is equal to T minus QV plus Q A dot V, and then we have a couple leftover terms, plus Q d lambda dt plus Q, in fact, let me go ahead and pull out the Q, plus Q d lambda dt plus gradient lambda, I'll put parentheses around it, dotted into velocity v. Well, interestingly, this is the complete time derivative. This is d dt of lambda of r and t. Okay, because partial lambda with respect to t, and then chain rules is going to give you gradient lambda dot dr dt, which is v. Okay, so yeah, make sure you see that. So we have equals d lambda dt plus gradient lambda dot dr dt. So there you have it. And so yeah, the gauge transformed potentials here deliver the goods here in our mechanics problem as well, because this is a very fundamental theorem of these Lagrangians. So this Lagrangian here is the original one plus a complete time derivative of a function of the position in time. Same as we said right there. Okay, good. That's a good place to stop for today. Oh, I had a little list of homework problems. I haven't gotten to all this yet, but I'm going to write them on the board. This will be our next set. Homework. These will all be chapter 10. I have here 1, 3b. Why did I say 3b? I don't know right now. 1, 3b, 4, 5, and 10. Put in a red box so they don't get lost. Good. There you have it. See you guys next time.